Hey everyone, welcome back. In the previous video, we had talked about how nitrobenzene can be made from benzene, how benzene sulfonic acid comes from benzene reacting with SO3 and concentrated sulfuric acid, how alkyl benzenes are made using the Friedel-Crafts alkylation using the FeCl3 or AlCl3, and similarly, how acyl benzenes can also be created from the same Friedel-Crafts catalyst but using a different reagent based on the requirement. In today's video, we're going to talk about these reactions including the Friedel-Crafts alkylation and acylation, and we're going to talk about their mechanisms. First, let's begin with the bromination of benzene. In the very first step, we do electrophile generation. We produce the electrophile, which is later going to be attacked by the benzene's pi electron system. So we take basically bromine molecules and we provide them the presence of FeBr3 catalyst in the anhydrous state, which is the Friedel-Crafts catalyst for us. What actually happens is that one of the bromine donates a lone pair to the iron atom and does the heterolytic bond fission. So one bromine becomes a positive ion, which is going to be the electrophile for our case, and the other bromine donates an electron pair to the FeBr3, making FeBr4 negative. Once the bromine positive ion, or you can call it bromonium ion, electrophile is created, the resonance thing happens. Now what happens? One of the carbon atoms from the bromine, let's suppose I'm numbering these carbon atoms from 1 to 6. Let's suppose carbon 2 picks one of the pi electron and gives it to the bromine electrophile. This disrupts the entire resonance, but at least carbon 2 makes a bond with the bromine atom. You can see the hydrogen atom is right there on the benzene ring carbon 2, which is for each carbon. In order to resume the resonance, the hydrogen atom has to be compromised. The hydrogen atom donates the electron pair from its bond pair, and hydrogen atom is eliminated so the resonance can be resumed. And what happens to the hydrogen atom? It becomes hydrogen ion and it is eliminated. In part C, we talk about the regeneration of the catalyst. The catalyst was FeBr3. So remember, the hydrogen ion which has been produced from the benzene, it reacts with the FeBr4 which was produced initially, FeBr4 minus I should say. The bromine atom from the FeBr4 minus makes a bond with hydrogen to make HBr, and the FeBr3 is produced. These are the products for our case. Let's talk about the name of the product. So that is bromobenzene, and the other was obviously hydrogen bromide. Let's talk a little about the nitration process. In nitration process, we are trying to make nitrobenzene. The electrophile generation is the first step. How do we produce the electrophile? So we take concentrated nitric acid and concentrated sulfuric acid. Both are acids, but sulfuric acid is slightly stronger acid, so sulfuric acid will donate a proton to the HNO3. Since sulfuric acid is donating proton, it acts as acid, and nitric acid acts as a base. Due to this reaction, hydrogen sulfate ion HSO4 minus is produced, while the nitric acid molecules splits itself into NO2 plus ion and water molecule. NO2 plus is the electrophile. We also call it the nitronium ion. Now NO2 plus is going to be accepting electron pair from the benzene. So part B is going to be the resonance, where the benzene molecule with its all 6 carbon atoms is going to react with the NO2 plus ion. Particular carbon atom donates an electron pair to the NO2 plus ion and makes a dative bond basically with this NO2, where the benzene ring resonance has been disrupted, but at least a bond has been made with the NO2. I should remove the plus because now the bond has been made. Remember that the carbon atom that donates the electron pair becomes sp3 hybrid temporarily. So this is a sp3 carbon atom which is making a bond with the electrophile. In order for the benzene to regain its stability, the benzene has to accept an electron pair. So hydrogen atom is eliminated and the electron pair from the bond is taken into the benzene resonance system. This way, a nitrobenzene is produced and the hydrogen atom is eliminated as hydrogen ion. How do we regenerate the catalyst? The catalyst, you should remember, was concentrated sulfuric acid. So what do? The hydrogen ion that is produced reacts with the hydrogen sulfate ion and produces sulfuric acid. So in this way, sulfuric acid is recreated and is able to catalyze another series of reaction. What happens overall is that the benzene ring reacted with nitric acid in the presence of concentrated sulfuric acid. What you get is known as the nitrobenzene and a molecule of water. Let's talk about the Friedel-Crafts alkylation, where the first step is also again going to be creating an electrophile. You take any alkyl chain you need with a halogen atom and you take a similar kind of Fe catalyst, which is FeCl3 or FeBr3. The chlorine atom does hydrolytic bond fission, gives an electron pair to iron atom. In this hydrolytic bond fission, basically the alkyl chain becomes a cation and the FeCl3 becomes FeCl4 minus. So carbon gets a cation known as the carbocation and you get FeCl4 minus. I should have written minus over here. I don't know why I wrote plus. What happens next is a very similar idea, that let's suppose these are the 6 atoms of the benzene ring. One of the carbon atoms donate an electron pair to the carbocation which was created earlier. Although this disrupts the pi bond resonance, but one of the carbon atoms successfully makes a bond with the carbocation, making it an alkyl chain. Now, in order for the benzene to resume its resonance, we need an electron pair, and we know what happens now, that hydrogen donates the bond pair and is eliminated as hydrogen ion. We have made a bond successfully with the alkyl chain, and now it's called alkyl benzene, or I should particularly call it ethyl benzene, and hydrogen ion is eliminated. How do we create the catalyst again? The FeCl4 minus reacts with the hydrogen ion and it produces HCl using the hydrogen ion, and the other thing we receive is the catalyst, which was FeCl3. You can see HCl and FeCl3 are recreated. This regenerates my catalyst. In Friedel-Crafts acylation, we have a similar idea where I produce an electrophile using a halogenoalkane or acyl chloride. In acyl chloride, I similarly use FeCl3 and acyl chloride, or you can call it ethanoyl chloride. The acyl chloride chlorine atom donates an electron pair to the iron atom and makes FeCl4 minus. What happens to the carbon of the acyl chloride? So it becomes a carbocation. Now this carbocation is basically my electrophile. What happens, what follows, is something we already know. A carbon atom from the benzene ring donates an electron pair to the carbocation, making a dative covalent bond, and this way the benzene ring resonance gets disrupted, and now basically this carbon atom has a bond with the carbocation of the acyl chloride. What happens next is, again we know already, the hydrogen atom bond, the hydrogen carbon bond will be broken down hydrolytically and the bond pair will be added to the resonance system. In this way, the benzene ring resonance is resumed, it is recreated, and the bond with the electrophile, which was the carbon, is still here. How do we recreate the catalyst? So that is something we already know so far, that the FeCl4 minus will make a bond with the byproduct, which was my hydrogen ion. The hydrogen ion will make a bond with the FeCl4. In this way, FeCl3 and HCl are produced. These are the 4 general reactions for benzene electrophilic substitution. Let's talk about some other reactions of the arenes, which may also be known as the side chain reactions. So when we talk about a benzene ring, one of the most common reactions is the hydrogenation using nickel 300 degrees Celsius, or you can say platinum is also a good catalyst over here. That is called hydrogenation, where the pi bonds are broken down and you create cyclohexane. So from benzene you produced a cycloalkane. The other common reaction happens when an alkyl chloride does alkylation, that we already know. With anhydrous FeCl3, you add the alkyl chain through electrophilic substitution reaction, for example methyl chain or ethyl chain, etc. This way you successfully produce a methyl benzene or ethyl benzene or perhaps propyl benzene. Now we already know this, why are we talking about this again? So let's suppose you made ethyl benzene. You can also produce 2 different compounds from this reaction. The first includes a boiling with whatever halogen for an free radical reaction. So let's suppose you boiled it with bromine in the presence of UV light. This is gonna be a reaction on the side chain, not on the benzene, because you're using UV light. So the ethyl group is gonna be brominated, and this way the benzene ring is still stable, but the side chain has been brominated. For example, there are 2 carbons on the side chain, so you can add a bromine on either of those. You can get multiple products based on the free radical substitution. So remember, the side chain is also capable of reacting. In this way, the reaction on the side chain was considered. Reaction on side chain because you're using UV light. We can talk about another reaction where we basically use alkaline manganate followed by concentrated sulfuric acid. So manganate is an oxidizing agent. It oxidizes the side chain to produce carboxylic acid group, and that is known as the benzoic acid. You can ask me that there were 2 carbons in the side chain, but why benzoic acid as a single carbon? No matter what the side chain is, you always get the same benzoic acid. You always get the same benzoic acid no matter how long the side chain was. The other carbons are eliminated as carbon dioxide. So always make the same benzoic acid. I hope these ideas are clear for you guys.